Hey everybody, this is Mr. Mazzoro again, and today I want to wrap up our talks about the chemistry of ocean water by talking about how light and sound affect ocean water, how light and sound actually travel through ocean water. We're going to talk about light first, and then how organisms use light to their advantage, and then we're going to talk about sound second, and how organisms use sound to their advantage. So, light. The light we see is reflected, and we don't see any light that is absorbed. If we're looking at, let's say, a red letter on a screen, don't know why I'm thinking of that particular example, but there you go. We're looking at that red letter because red light is hitting that letter, and that red light is being reflected to our eyes. Blue light and green light and orange light might also be hitting that letter, but the red color in that letter is absorbing those colors of light. As a result, we don't see them. If we take these definitions, then what you'll note that white is white isn't the absence of light. It's, in fact, all the colors of light. Red, orange, yellow, green, blue, indigo, and violet. All hitting an object, being reflected to our eyes. When that happens, when all the colors of visible light hit an object and are reflected to our eyes, we perceive that object as being white. And the opposite of white is black, when all the colors of light are being absorbed. No visible light is being reflected. So a little practice with this concept. If we have white light and it hits an orange shirt, the color of light that's reflected is orange. That's why we see that shirt as orange. And all the other colors of light, red, yellow, green, blue, and violet light, are all being absorbed. If we have white light hitting a white board, all the colors of the light are being reflected to our eyes. That's why it's perceived as being white, whereas no colors of light are being absorbed. Vice versa, if white light hits a black pair of jeans, that means that all the colors of light are being absorbed and no of the colors of light are being reflected. That's why we perceive that as black. Why are we studying this for marine science? Well, it has to do with this scenario. Deep water tends to be blue. So what happens if you're not blue? Let's say you're wearing a red shirt in a room with only blue light, or an ocean with only blue light present. That blue light hits that shirt, but the shirt's red. It's going to absorb the blue light. So no colors of light are being reflected. And the blue light is being absorbed. So if no colors of light are being reflected, what color do we perceive that shirt, even though it's red in a blue room? The answer is the shirt would appear black. Why? Because there's an absence of light. No colors of light are being reflected. It's not violet, it's not brown, it's not blue, it's not red. We would perceive that shirt as being black because we perceive the absence of light hitting our eyes as black. Water doesn't absorb light evenly. Some colors of light become absorbed faster than others. Specifically, red becomes absorbed first, in barely any depth at all. At about 33 feet down, there is no more red light left. Anything that would be red down there would actually appear black because there's no red light to reflect. Deep water is blue because the last colors of light to be absorbed are blue and green. And that's the reason why water is blue, is because it reflects blue and green light the most. It's the blue and green light are the last to being absorbed. It's also why the deeper water is, the deeper blue it appears. How do organisms use this? Well, smaller organisms that are lower on the food chain, they tend to be red in the ocean. If you remember, they're basically the red shirt in the deep blue ocean, and as a result, they appear to be black. These organisms in deeper water where there is no red light, or from farther distances away where red light would be absorbed, would appear black and therefore have an easier time blending in with the dark, deep ocean. They wouldn't be blue, and the reason is because they would be reflecting blue light, and that's the only color of light that's present. They would actually stand out if they were blue. Camouflage in the ocean is done by being red, not blue. Next, I want to talk about sound in water, and how organisms use sound in water. There's really only one type of organism that uses sound in water, and that's marine mammals. We're the only organisms in water that have ears the way that we understand it, that actually perceive sound. Marine mammals use sound for echolocation, and they also have songs that they use for mating purposes. So if you want to mate, and you're going to mate as a marine mammal, a whale or a dolphin, by singing, ideally you want your song, your mating song, to reach as many females or males as humanly possible, as dolphinly or whaley possible, I guess. The reason is because the more whales or dolphins it reaches, the more potential mating opportunities you'll have. So how can you make sure that your song will reach as many mates as possible? Well, the answer is we have to slow sound down. Why? Well, because slow moving sound travels farther in water. Slow moving, low frequency sound will move a lot farther through water than high frequency, fast moving sound. And here's why. If I show you a high frequency, fast moving sound wave, it has a shorter wavelength, and as a result, if it encounters something like a fish or a rock or anything, it just gets absorbed by that object or reflected. It doesn't travel past that object. Not nearly as well as low frequency, slow moving sound with its larger wavelengths that has much more of an ability to move through objects or even around objects. You've probably noticed this. In the winter, if your windows are closed and someone pulls up next to you and they're blasting music through the radio, you don't hear all parts of the music. You hear the bass of the music. That's because the low frequency, slow moving sound, the bass, has the ability to travel through the glass and metal of their car and the glass and metal in your car and get to your ears better than the treble, the high frequency, fast moving sound. So what two characteristics are what is going to slow down sound in water to make it slow moving and low frequency sound? The answer is temperature and pressure. Temperature and pressure both affect the speed of sound through water. And if you're a whale and you want slow moving, low frequency sound, where will temperature and pressure combine in the best way to slow sound down the most so your song of mating goes the farthest? Well, in order to answer that question, we have to take it apart. I'm going to show you 3 ocean profiles. The first, the one you're looking at right now, actually has the speed of sound through water on the x-axis, the depth of water on the y-axis, just like you're used to looking at. But I'm only taking in consideration temperature. We're pretending pressure has nothing to do with the speed of sound through water. So, looking at this graph, where's the slowest moving and therefore farthest reaching sound? The answer is it's towards the bottom, down here. If you just take temperature into consideration and you were a whale, you'd want to sing in deep, deep water because that's where the slowest moving sound will be, and therefore the farthest your songs will go the farthest. Now we flipped it. Now we're just taking pressure into consideration and pretending that temperature doesn't have anything to do with it anymore. Where's the slowest moving sound now? Well, it was at the depth, but here you look, deep water has fast moving sound now. Just taking pressure into consideration, our slowest moving sound is in shallow water. Pressure, if we're a whale, wants us to sing in shallow water. Temperature, if we're a whale, wants us to sing in deep water. So where do we end up singing? Well, if one wants us to sing in the shallow and the other wants us to sing in the depth, the answer is we sing in the middle. If we take both temperature and pressure into consideration, which is a realistic, real-world scenario, you'll note that the sound slows down the most in the middle area. That's where temperature and pressure combine to slow down sound the most, which means that our songs in that area will travel the farthest. This area is known as the SOFAR channel. It stands for Sound Fixing and Ranging Channel. And it's a layer where whales preferentially sing their mating calls because they have learned through generations and generations and their parents and parents before them that those songs that are sung in that area actually result in more mating opportunities. Those whales that sang in the shallows or in the depths, they still sang, but they had less mating opportunities, and over time they died out. The reason sound slows down the most in this area, again, is because temperature wanted us to sing in the depth and pressure wanted us to sing at the surface. So when we combine both temperature and pressure, we get an area in the middle where sound slows down at a maximum and therefore travels the farthest. So We learned that light travels through water unevenly. Blue and green light go the deepest. That's why deep water, appears blue and green. And red light doesn't go deep at all, which is why small organisms in the ocean tend to be red. Because in the deep ocean, there is no red light, and the absence of light to reflect makes them appear black and helps them blend in. We also talked about slow-moving, low-frequency sound traveling very, very far through water. And temperature and pressure are going to combine to slow down sound in the intermediate zone, which means that whales will sing in the intermediate zone preferentially in order to get mates, because they've learned over millions of years of evolutionary history that the songs in that area will be met with the most mating opportunities. So that's it for the chemistry of water. I hope that you've learned something specifically about light and sound in this lesson, but other things in the future. In the next unit, we're going to talk about ocean ecology. We're actually going to move away from kind of the non-biological stuff and start talking more about the ecologies of the oceans as a whole.